Good morning, ladies and gentlemen. I hope you are doing very well today. For today's class, I have apparently skipped all the way to Unit 8. I don't think you want to do Unit 8. That is the hardest unit. So let's mosey on back to Unit 2 real quick. Sorry, Unit 3. For today, I figured I would go through some of the problems I asked you to do yesterday. Which actually, really quick, let me check if you actually did them so I can scold you in class if you didn't. Let me see. Okay. Noah, Lily. Oh, hold on. Is this? Hold on. This for some reason is not including the ones I assigned yesterday. Here we go. Oh, okay. None of you have done the properties of solid quiz yet. None of you have done the intermolecular forces one yet. I'm hoping that changes before tomorrow. It is only 8:30. I guess I'll give you some time. But I'd like to keep in mind, for some of you, I want to know I can, see whether you have done stuff or not. Also, I know I left time at the end of class yesterday to watch some videos, and I can see that most of you did not even start them. I can actually see the exact percentage of the way you got through them. Chloe getting 54% of the way through video 3.1. And Garrett with 84% of video 3.1 number 2. So, just want you to keep in mind, I can literally see the exact percentage you've watched. Do the homework. Alright, I can't grade these for accuracy, but I can grade them for credit. So don't make me start giving you Fs on homework. This is an AP class. I want to focus on the content. Let me focus on the content. All right. With that out of the way, with that stern talking to, I'd like to go over some of these, but I realized I actually did not talk about two of the properties under intermolecular forces, and I figured I would just pull up the video and scroll to the part the stuff I didn't talk about, and I'd like to expand on these more. So let me turn on my board. We have vapor pressure, right, and volatility, and these are intrinsically related. I forgot to talk about these. So, if something is volatile, that means some of it evaporates. Let's imagine you have a closed container of water, or of a liquid. Let's say one is water, and the other is gasoline. Let's pretend those are the same size containers, even though they're definitely not. They are each going to have some degree of volatility, some ease of evaporating. So, you'll remember this actually directly relates to scroll back. This directly relates to melting point and boiling point. When something boils, you're fully changing the phase to gaseous. And it's more of a dramatic event than slow evaporation. In this, energy is overcoming the intermolecular forces holding the molecules together. The more intermolecular forces we have, the higher the boiling point is. The harder it is to evaporate because you have to overcome those forces. So now we can look at vapor pressure and volatility. If something has higher intermolecular forces, it's going to be less volatile. If the forces holding them together are stronger, they're not going to come apart, right? Because that's part of moving into a gaseous phase, is coming apart from the rest of it. So vapor pressure is pressure that's caused by the gas when it evaporates. So if we have those containers I mentioned, and let's say we have water and gasoline. Water has far more forces. In fact, water has hydrogen bonding, whereas gasoline just has London dispersion forces, LDFs. So you should expect to see some water molecules in the air above any sample of water, but far more gasoline molecules. Because we have more molecules here, you're going to have a higher vapor pressure here. Because this gas is going to be exerting a force on this water as well as the container. Not the water, the gasoline, right? The gaseous gasoline is going to be exerting force on the liquid and the container. Water will be exerting a force too, but it will be exerting a smaller force. I forgot to cover that yesterday. That's really the only thing, but again, some place you might see this is it might, you might just be given a table with vapor pressure or volatility of two liquids and asked which one has greater intermolecular forces. So this is important to know. Vapor pressure and volatility. I meant to underline those, not cross them out. My apologies. So the more volatile something is, so again, the less force there is holding something together, the less force, right? LDFs are smaller. The easier it is for them to separate and become gaseous. The more things can become gas easily, the more volatile something is. And the more gas molecules you have, the higher the vapor pressure. All right. So with that, let's actually talk about these problems that you all should have done by tomorrow, and I will be checking first thing in the morning. Well, I'll check right before class. This is a model of gaseous diatomic elements. It says it's just about boiling point, so we know they are gases. Intermolecular forces will cause them to condense into a liquid phase if the temperature is lowered, which the following best describes how the model is limited in its depiction of the phenomenon. So let's look at each of these options. How is this model limited in depicting this? We have a couple options. It does not show how hydrogen bonds are constantly forming, breaking, reforming, which results in a net force of attraction. It does not show how the interactions between ions and induced molecular dipoles result in a net force attraction. It does not show how the interacting permanent dipoles of the molecules result in a net force attraction. And it does not show how the temporary fluctuating dipoles of the molecular electron clouds result in that force attraction. So basically what it's asking you here is what kind of intermolecular force do these molecules have? That's the heart of the question. Right. What it's pretty much saying is if it goes down into a liquid phase, then they'll have intermolecular forces. But it's not showing that they do have some intermolecular forces in the gas phase. Which intermolecular forces are they? Well, it's not hydrogen bonding. We know we have a diatomic gas element. For hydrogen bonding, you need hydrogen with nitrogen, oxygen, or fluorine. We could have hydrogen, we could have nitrogen, we could have oxygen, we could have fluorine, but we can't have hydrogen and one of those other ones because it's just one element. So it can't be hydrogen bonding. Next, we can look at ions and induced molecular dipoles. We don't have any ions, so it can't be B. Finally, we can look at C. Permanent dipoles. We cannot have permanent dipoles here because it is a diatomic element. That means both of these atoms are the same element, which means they both have the same electronegativity. So there's no difference and there's no dipole. The only thing that we have is temporary fluctuating dipoles. Right, our London dispersion forces. Or induced dipoles, right? So our answer is D. Next, we can look at this other question. Electron cloud of HF is smaller than F2. However, HF has a much higher boiling point than F2. Which of the following best explains how the dispersion force model of intermolecular attraction does not account for the unusually high boiling point of HF? So, we're not talking about comparing dispersion forces. Instead, well, let's look at these. To have a higher boiling point, it has to have higher intermolecular forces. Right? It holds it together more, it makes it more difficult to boil. So we can look at what would cause each of these. Or rather, what intermolecular forces these have, right? Without even looking at our options. F2, two elements, two of the same element. There's no dipole at all, there's no polarity, so all we have are L London dispersion forces, LDS. HF, however, we have hydrogen and fluorine. That means we have hydrogen bonding. So, liquid F2 has weak dispersion force attractions between its molecules, whereas liquid HF has weak dispersion forces. Well, that's true, it does still have those. You could actually end up with even more, an even stronger dipole due to random fluctuations, but it also has hydrogen bonding. So dispersion forces alone doesn't account for the boiling point because we also have hydrogen bonding. Then we have 4 different liquid compounds in flasks at 20 degrees Celsius are represented above. The table below shows or identifies the compounds. Flask C shows the most particles in the vapor phase, which the following is not shown in the model, but best helps explain why flask C must contain the element pentane. Well, let's look at each of these and think about what that means, right? These are our boiling points. We have 4 of them. And let's go beyond identifying this as pentane and let's identify all of them. Remember, as intermolecular forces go down, as intermolecular forces increase, vapor pressure decreases and boiling point increases as intermolecular forces increase. We have a lot of things in the gas phase here, in the vapor phase. That means we must have a lower boiling point that's easier to overcome. And we have a higher vapor pressure in flask C. So to have a higher vapor pressure, we have to have a lower boiling point. It's the one with the most gas particles, so it has to be the one with the lowest boiling point, pentane. Now we can just go through and identify all of them. 69 should be the second highest, D. 98, third highest, B. And 126, octane, should be the fourth highest, A. So, all right, octane, heptane, pentane, and hexane. Now we can also talk about why we see this increase. There is no change in polarity here. We don't have any polar bonds here. It's all carbon and hydrogen, which are almost the same electronegativity. So all of these are based on London dispersion forces. But remember, when something gets longer, it has increased London dispersion forces just due to random interactions. So, highest, lowest. So now let's look for our answer. Which of the following helps explain why flask C must contain pentane? The random motion of the particles within liquids. I mean, all liquids have that. That doesn't really make sense. Relative speeds of the vapor particles in each flask. We don't know. Actually, no, we do know. Sorry. All flasks are at 20 degrees Celsius. If you remember, temperature is kinetic energy. They all have the same kinetic energy. Having the same kinetic energy, pentane will actually be slightly faster because it has less mass, and potential energy is equal to 1/2 times mass times velocity squared, but it will not be significantly faster. And again, that doesn't really have anything to do with why this has to be C. The strength of intermolecular forces between the particles in the liquids, right, and the structural formula of the molecules. Well, the structural formula itself doesn't have anything to do with it, but rather the strength of the intermolecular forces does. Now, this one should be a pretty easy guess since we are in the intermolecular forces chapter. But really, what it's caused by is just the fact that it's longer and has more opportunities for those random forces. Or in this case, pentane is shorter. It has fewer opportunities for London dispersion forces to form, so it has fewer forces. It has a lower strength. All right, we are at 18 minutes. Let's do a little more. I'm feeling a little bit tired today. Sorry, long few days. So I'm just going to teach pretty much off the video. I'm going to mute and I'm going to scroll through just because they also have better pictures than I do anyway. I'd like to expand on the pictures. So for this chapter, we're talking about types of solid compounds. Ionic. We have our positive, negative, positive, negative, positive, negative. Positive and negative ions holding each other together. We have molecular. Molecular compounds are just held together by the intermolecular forces, right? Metallic compounds, we just finished talking about how metallic bonds form, right? The sea of electrons. And then we have something called covalent networks. That is where you have a large repeating network. It's kind of like a cross between an ion and a molecule. And actually, a diamond is a perfect example of one of these. Instead of one small molecule, you have this big repeating network of molecules over and over again. A lot of gems have this. So for example, ruby chemical structures. Chemical structure of ruby I'm sorry, I was thinking of a different gem. Rubies are actually themselves an ionic compound. I can't recall what gem it is off the top of my head, so I'll get back to you on that, actually. It is aluminum oxide. In fact, it actually would be possible to... I can't remember the structures for these. Let me see. I think amethyst would be one. Amethyst, quartz, other silicon oxides. Yeah, let me see if I can find an image of its long form repeating structure, though. Can't seem to find a good example of one. They're mostly showing diamonds and graphite. Even that's showing diamonds as well. Okay, well, let's come back to this some other time. Covalent networks, it's basically just a bunch of covalent bonds forming a crystalline structure that goes off in every direction, continuously repeating. Graphite's another example of that. So, again, ionic solids, right? Positive, negative, positive, negative, positive, negative, in a three-dimensional lattice. A few properties of these. First off, a simple ratio based on the formula. High melting point and boiling point. The reason for this is we're not just looking at simple intermolecular forces. They are full bonds. So although covalent bonds are generally stronger than ionic bonds, we're not just looking at breaking and melting, right? We're not looking at melting covalent bonds when we're melting covalent molecules, molecular, right, solids. We're looking at overcoming the intermolecular forces. So these are full bonds holding everything together. There's no intermolecular forces really at play here. So, right, these are actually going to be stronger and result in a higher melting point and boiling point. And they are brittle for the same reason, right, that I've previously talked about, right? They are brittle because, again, if you physically push and overcome the force, the forces holding these together with physical force, you're going to cause it to come out of alignment and then pop right out. And lastly, again, poor conductors, you need free flowing conductivity, free flowing charged particles. These are stationary. They can't flow freely. You melt them or dissolve them, they conduct. But as solids, they do not conduct. So, molecular solids, right? Individual molecules. They are held together in a lattice structure that is formed by intermolecular forces. They're pretty much entirely made up of non-metals. And unlike our ionic solids, where the formula is a ratio, these ones are actually the number of atoms in each molecule. they have much lower melting and boiling points, because again, all you need to do is overcome the intermolecular forces, which even at their strongest are going to be weaker than ionic bonds. They are always poor conductors of electricity, as non-metals tend to be insulators. All of the electrons are held in the covalent bonds, not allowing them to move about freely. So, covalent network solids. These are formed by distinct atoms, all bonded together covalently in a 3D network. So, again, what that means is each is an individual atom not held together by charges. They're not ions, they're atoms. They are bonded covalently, but again, not a simple molecular structure. They go out in a long-range repeating structure. This is mostly formed by carbon and semimetals, although it can be formed by other compounds. High melting point and very hard. These are also generally poor conductors of electricity for the same reason. However, in certain cases, certain covalent network solids can be good conductors of electricity. That's more of an exception, so don't worry about that. Graphite is another example. Graphite's actually really cool. You will see a lot of people kind of have conspiracy theories about graphite. One really neat thing, graphite makes an essentially impenetrable barrier that no chemicals can pass through. The reason being, these are double bonds here. Now it doesn't want to go. Come on. Come on. Sorry, I'm getting annoyed at this. It is not letting me draw. For some reason, it's putting everything over here. Let me see if I can do this now. Only out to here. Sorry, let me see if I can. Apparently it only wants to let me draw on the left side of the screen. Okay, well, imagine we have double bonds around all of these. You have a high amount of electron density here. So anything trying to pass through this barrier will be repelled. Furthermore, it's a small space, so things that are too large can also not pass through. The only thing I'm aware of that can pass through is hydrogen ions. Hydrogen ions are able to pass through because they are positive. And because they're positively charged with no electrons, there's nothing to repel them. I imagine alpha particles, which are helium ions, would also be able to pass through. Those are pretty rare, but you can still see them in some cases. You can still see them in why am I drawing a blank? You can see, you see them in radioactivity. All right, and finally, metals. Formed by metallic elements only, as you can probably imagine being metals. Right, they have metallic bonding. Pretty straightforward. They're malleable and ductile. Right, you can shape them. Their melting point varies depending on the metal. It really depends on the strength of the metal itself. So again, gallium you can melt in your hand. Steel, that is a lot harder to melt. Aluminum, you can melt that in your fire pit. They conduct electricity very, very well because of the free-flowing sea of electrons. So where are we at? 31 minutes. All right. Let's go over some questions surrounding these that I also asked you to do for homework. Which statement best helps to explain the observation that NH3 boils at negative 28 degrees Celsius, whereas pH3 boils at negative 126? In this case, we have phosphorus and hydrogen. Phosphorus. Now, you don't need to have these memorized, but it's good to look them up as a reminder of where our more electronegative elements are. Phosphorus is at about 2.19, where hydrogen is about 2.20. So that's not really electronegative, right? Our electronegative elements, the ones that are actually going to create electronegative interactions, are really nitrogen, oxygen, fluorine, chlorine, and to some extent bromine. Slightly iodine. Pretty slightly. Right, but it's pretty much these that we actually want to look at for our intermolecular forces. And really, when we're looking at iodine, it's probably going to be comparing iodine to bromine, chlorine, and fluorine. When we're comparing, and then you're probably going to be comparing nitrogen, oxygen, and fluorine going this way. As you go further to the right, you get more intermolecular forces. You get more electronegativity. As you go further down, you get less electronegativity. So you're probably going to see these compared and these compared. Or in this case, phosphorus and nitrogen compared. Phosphorus is a row down, so even if you don't know the exact value, you know that it is less electronegative than nitrogen. And nitrogen, already being one away from carbon, is really going to be the least electronegative of the more electronegative elements. So, NH3 has hydrogen bonding. Hydrogen bonding, right, is between hydrogen and then nitrogen, oxygen, and fluorine. The HNOF. Hydrogen bonding is stronger than the dipole-dipole forces of pH3. Now, they really are around the same, so it's going to be debatable as to whether or not it's going to be more like dipole-dipole, or if it's going to be, right. Well, for this, actually, let me show you. I don't know why it's not working half the time, and it is pissing me off. So let me open that in a pop-up. All right, pH3. Going to have something like this. Because we have this extra pair here, there's more electronegativity on phosphorus, giving it a negative charge. Right? It makes for a polar situation. Not hugely polar, but slightly polar. That creates a dipole. All right, let me get rid of this. All right, so NH3 has hydrogen bonding that is stronger than the dipole-dipole in pH 3. All right, well, let's come back to this one more closer to the end of the chapter, actually. For this one, we have ionic compounds. Sodium chloride and magnesium sulfide are represented in the diagrams above. Which statement correctly identifies diagram 1 and identifies the compound with the lower melting point, explaining why? Well, let's look at each of these. We see, right, an ionic compound, one thing connected to another thing, right? 1, 2, 1, 2. Nothing out of the ordinary yet. All right, however, if we look again, hold on, I want to see if there's any more information. It correctly identifies diagram 1 and identifies the compound with the lower melting point. So first off, let's think about which one would have the lower melting point. Lower melting point correlates to a smaller strength of forces holding it together. A weaker bond is going to be one between a +1 and a -1. So lower melting point, right, is going to be sodium chloride. So we can already eliminate C and D. Diagram 1 says it has a lower melting point than NaCl. It has a lower melting point than NaCl. So instead, right, we know that sodium chloride has a lower melting point than magnesium sulfide. Now we have to ask why. The Coulombic attractions between singly charged NaCl are stronger, or they are weaker. They are weaker. So our answer is B. All right, the structure of one form of boron nitride is represented above. The form of boron nitride is one of the hardest substances known. Which of the following explains why boron nitride is so hard? So, one, you should remember, one of the ones we just talked about is very hard. Right. Also, I just exited out of obituary. That was for a different Mike O'Brien. That is not the Mr. O'Brien from Bishop Stang, so don't go spreading rumors around that. That was for somebody else. Anyway, my apologies if anybody saw that and was like, what's going on? No, that is not the case. Boron ions are held together by ionic bonds. Well, we can look at these. These don't look like ionic bonds. We can see the bonds there. Those are representative of covalent bonds. Right? Boron nitride is an alloy. Alloys are not bonds, right? Or they're not held together by covalent bonds. Those are metal bonds or metallic bonds, right? Boron nitride is a polymer, or boron nitride is a network solid of atoms. Well, a polymer is a long chain repeating in structure, where a boron, but really it's one chain going in one direction. Whereas a covalent network goes off in every direction. If we look, this is going off in every direction. Going on this way, it goes up, presumably it would go we can see it going forward and backwards. It's going in every direction. So this is a covalent network. Covalent network compounds are the hardest substances. That's why diamonds are so hard. All right. We're just at about 40 minutes. So for your next homework, right, I already asked you to watch the solids, liquids, and gases. I'll go over those next chapter. I'd like you to watch, and we've already pretty much done this. So this should really be review for you. But watch the videos on the ideal gas law, as well as try out the topic questions on those. You can do them. I know you can. All right. Have a great day, everybody. See you all soon. I will be back next week. I'm looking forward to it. Have a great night.